Welcome to Maastricht, welcome to the ETpathfinder, our little prototype for the next generation gravitational wave detector, the Einstein Telescope. I will show you around our nice clean room that is behind this wall, but before we can go in there, of course, we have to dress up because humans are very dirty, clothing is dirty, so we wear this nice bunny suit, it's a scientific term, together with gloves, with special shoes, that keeps all the stuff that is on our clothing away from the clean room, but it's also easily cleanable. For that, we go into this air shower that will blow off all the dust, and then we are ready to go into the clean room. So now we enter the big clean room. There's actually people working here, which is nice to see, I guess. And here you can see the big vacuum system. All these steel tubes and these big steel tanks are the place where we house our laser interferometer, which we use to test technologies for the next generation of gravitational wave detectors. And maybe we can have a little look onto this chart. This is kind of the same orientation as you have here. We have 1, 2, 3, 4, 5, 6 towers in total. This tower here on the right, if you look to the right, is the furthest tower there. Exactly. And then we have the next tower rising up here. That is the so-called beam splitter tower. You can see that here. And then we have this arm with these two towers. That's down this direction. And then the same in the other direction. So in the first tower here, we will put the lasers outside in front, bring the light inside, and then have some stabilization, so we have stable laser light. That will then go into this beam splitter tower, so into this tower here, where the light will be split in half, and then will be directed so that both beams will go down this arm, and this will be for one laser, but we have a second laser with a different wavelength, and we do the same game, stabilize the laser there, split it here, but then send both beams down the other arm. And what will happen in the arms, I will show you once we go there. So here you can see one of the arms. It's roughly 10 meters long and has these huge towers that are necessary. Why, I will explain in a second. But first of all, so the laser light will come through the tube into the first tower, hit a mirror. Part of it will be transmitted, go through this tube into the second tower, hit another mirror, and then bounce back and forth between these two mirrors a few hundred times before it comes back to the beam splitter tower. And there we compare how long each of these beams took inside this tube, and then we can measure exactly how far away from each other these two mirrors and the beam splitter are. And that's our measurement, what we want to do to test the technologies, the sensitivity that you need in then the big scale experiment, not 10 meters, but 10 kilometers in the Einstein Telescope. A further complication that we try to examine a little bit is we want to go cryogenic. So each of these towers here will house a mirror that is inside a cryo chamber. So we will cool down the mirrors in this arm to temperatures of 120 Kelvin, or roughly minus 200 degrees Celsius. In the other arm, even more, minus 250 degrees Celsius. So really, really cold. And we want to see how well that works and what complications we get. In order to get a good vacuum, we need a lot of vacuum pumps. For the main work of that, we use these, if you come a little around, so-called turbo pumps. These big blobs on there. They work like basically a turbine from an airplane. They have like a shovel thing that rotates very, very quickly and sucks out all the air and leaves us at pressures of a very, very small fraction of the atmospheric pressure. In scientific terms, we're going down to the 10 to the minus 8 millibars, so it's a very, very low pressure, very few molecules left. Nice environment to do sensitive measurements in. Now we get around the end tower to get into the inside. And as you can see, there's many more of these turbo pumps. So lots of installations that you need to get the proper vacuum in there. And here you also see tubes that contain liquid nitrogen that is used for the cryogenic operations. And you see all these tubes and connections here are all to supply the vacuum system with all the required pressure, temperature, and all the electronic signals. And we're still in the process of setting everything up, so it will become even more messy. And here you can see that basically the second arm looks roughly like the other arm, so there's not a big difference, except for that here there's a little more cryogenic insulation to be able to go down to these very low temperatures. So what we want to do is we have these mirrors where we bounce the laser light off and we want to measure their distance. But as you know, Earth is always moving. Although it's only a few micrometers on a good day, this motion is way too large to be able to measure these very small displacements that we want to measure. So what we came up with is we use pendulums to make sure that the ground motion doesn't really move the mirrors. How does it work? So if you have a mirror here and it is suspended by some cable, then you have certain things that could happen depending on how fast you move it or what the frequency is that you move it in. If you are very, very slow, it will just move as much as the point from which it is suspended. If you're in a very unlucky situation, you have this frequency where you have this resonance, so you move only a little and it moves a lot. But what we are interested in is higher frequencies. So if I move really fast, this one does not displace much. But already you see that I have to move it quite fast. But what if we make it a bit longer? Here I can do it at quite a low frequency and still it moves very, very little. And that's why we have to do these big towers. We do a few of these pendulums on top of each other, and we need the length to be able to have this very, very still mirror hanging down here, and a lot of extra stuff that's up there that is suspending this mirror with this principle. Now we can have a look at the extra installations that are around the ETpathfinder, mainly the laser corner, where we are setting up lasers and playing with their properties and trying to characterize them so they are ready to be installed in front of the towers. And then we will also see how we do get these big parts of these towers inside of this clean room. So here we are at the laser corner. That's where we try to work on the lasers and also some other side projects. And as you can see here, no laser is on at the moment, so we can just walk in there without any extra goggles and protection, which is quite nice. I mean, you would still see it, but I would have some problems because the glasses are quite dark and they fog up easily, so it's a bit tricky to work here. As you can see, people are installing electronics around here. There's a lot of work still going on. And on this table, you just see a gray box, but this is one of the lasers that has been provided to us by Hanover, by the Max Planck Institute there. They built very nice lasers and they came here, brought it here, and are now testing it here and making it ready so it can go to the towers once we have the optics inside, and then we can do some interferometry. There's also some side projects looking at some of these suspension systems. I told you about the big towers that have the huge suspensions for the large mirrors for the main interferometer. But there's also a lot of extra optics that just steer the beams around, and they will be on these smaller versions of pendulums that can then be placed on some optical tables inside. But it's the same principle. You have these mirrors and some masses that have fibers in between suspending them. So you basically have a stacked pendulum in a small version and a lot of actuators and sensors around it to stabilize it and to be able to manipulate it. So this is the basic principle that we always use with these mirrors to make sure they are really, really still, but also controllable. The other part that we do here is doing some side experiments that deal with the fundamental properties of light. Light consists of these photons, so these basically energy packages, and they have some peculiar properties that they appear in a very random way when you try to measure them, and that makes an extra noise contribution in these sensitive measurements. And here we try to set up an experiment that finds ways to make the light a bit more smooth, a bit more even, a bit more predictable to reduce these noise sources. So in the end, it's just a few PhD students standing here, turning knobs, moving mirrors a little bit, but it's pretty fancy work. And now go into the area where we actually bring the parts of the towers inside. So if you look at the tower again, you see there's these seams here. They're bolted together. So you have these elements that are roughly a bit more than 1.5 meters in size. Also there, also on top of that, also on top of that. So the towers come in here piece by piece. If you look straight up, you see our big crane that was used to hoist them inside. But the question still is, where do they come from? And that's what we're going to see now. Another air shower. But this time we are going into the dirty part, so we don't need to get air showered. And this is the so-called goods reception. That's where we bring in the dirty stuff from the outside world. You see there's an overpressure that pushes this soft gate a little bit outside. So whenever you open it, there's an airflow to the outside, so no dust comes in. And we can bring in stuff through this gate inside of this room, clean it very, very well so it can go into the clean room. And then if you look up, there's this opening that we can lift off with a crane. So we have a big hole inside of here, and then we use the crane to take whatever we want to get into the clean room from here, lift it up, and then move it to its destination. It's a very nice way and very space-saving way of getting stuff inside without having to open the gate directly to the clean room, potentially making it very dirty. But there's also another reason why we have this area here. We have this extra room, and this is where we have the noisy pumps. So I showed you the turbo pumps that make our nice vacuum, but they need pumps behind them that really drag out the air, and they are really loud and noisy and big, and they are hidden inside this room that's a bit isolated from the rest of the clean room, so they don't disturb us. Also, a lot of the electric installation is hidden here, so everything that can be disturbing and noisy is away from the main experiment. Now we can go back into the main clean room, and here we are again on this side. Maybe one last thing that's really nice to see from here is our visitor gallery. This is up there. This is a room that is being used for outreach activities, having visitors, giving presentations. And when they're there, they can nicely look into the clean room without having to dress up like us. And also, we don't want too many people in this clean room because even if I dress up like this, I will bring in some dirt, so we try to keep it to a minimum. But if you stand up there, you can see whatever's happening inside and enjoy, have a good time, and learn something about physics. So I think this is it. That's all I can tell you in this short video format over our clean room. I hope you got a nice overview of how our vacuum system looks like, what we try to do inside, why it needs to be like that high and big, and why we need all these installations. And I think we can go back through the air shower again and then finish this. And on the way out, we can actually go in here with 2 people because we don't need the air shower again.